Hello, and welcome to Behind the Scenes, where we take a closer look and a deeper dive into our course material. And here I want to talk a bit more about section 2.6. And I want to make some comments that even go all the way back to section 2.4, where we're talking about the homogeneous variant on our differential equation. So let's remember what that is. That's m times x double prime plus c x prime plus k times x equals 0. So if we're talking about free motion here, then there's something actually very interesting that I can say. I can say that in any case, we have a decaying function. And I can actually show why this is. So one thing to start by mentioning is that m, c, and k are all positive. Now they could be 0, but if they're 0, that means that that element of the system is missing. For example, if c is 0, that means no dash pot. We've detached the dash pot. Now if k is 0, that means there's no spring attached. If m is 0, that means there's no mass, and so there's really no point in even talking about the system involving the mass. But otherwise, if these things aren't 0, they're all positive coefficients, right? M, the value for the mass, is going to be positive. C, the dash pot constant, is going to be positive. K, the spring constant, is going to be positive. And any minus sign would indicate a different direction, right? But so we're going to say with our differential equation, any value that we have for m, c, or k is always going to be positive, provided that piece actually is there and working. But what this does, so what I want you to notice from this is that when I build a characteristic equation, mr squared plus cr plus k equals 0, when I go to find the roots on this, I'm using the quadratic formula. So here, this is acting like b, so that's negative c plus or minus the square root of c squared minus 4 times k times m, all divided by 2 times n. And there's a few things that could happen with this, all depending on the discriminant, the stuff under the square root. Either the stuff under the square root is positive, and we get 2 distinct roots, or the stuff under the square root is 0, and we get that repeated root, or the stuff under the square root is negative, and then we start talking about imaginary values. Let's break those up into those 3 different cases. So we'd say, okay, well first, if c squared minus 4km is negative, and we talked about what this means for damping for the system, but let's just think about it in terms of building a solution. If this is negative, then that means I'm going to have this imaginary part to my solution. And in general, if I want to try to explain this quickly, my solution is going to look like x equals, I have e to the power of, it's the real part, which is negative c divided by 2m times t, times, in parentheses, now I'm going to have my sinusoidal stuff, because that's my complex piece here. So we'd say, well, some constant c sub 1 cosine of, something times t, plus c sub 2 sine of, something times t. Without trying to belabor the point, I get these oscillatory functions. But I want you to notice that, since we said c and m are positive, negative c divided by 2m is negative because it has this minus sign. So I get this exponential piece right in front. And so although cosine and sine are going to be oscillating, they're going to be oscillating while being sort of decayed by this exponential function. So the idea is that this is still going to tend to 0. And if I wanted some quick visualization of how this looks, we'd say, well, these oscillate while this exponential function brings everything to 0. Let me get a different color. Green. Is green good? So oscillating, but decaying as well. So eventually heads to 0 is sort of the idea. So that's one of the possibilities. Now, what if the stuff under the square root is 0? So I'd say, well, okay, that sounds good, but what if c squared minus 4km is equal to 0? Well then, in this case, I'm just left with negative c over 2m for the roots. So I get this repeated root. I get root r1 is negative c over 2m, and root r2 is negative c over 2m. And when I go to build my solution, we have to be careful with the repeated roots. We would say x is equal to, some coefficient c sub 1, and then e to the power of negative c over 2mt, plus, and then some constant c sub 2, and then e to the power of negative c over 2m times t. But this is not linearly independent. These are linearly dependent. So here I have to multiply by a t here. But in this case, we still have a function that, as t goes to infinity, so in both of these cases, as t goes to infinity, the function x tends to 0. And that's true here when I have the sinusoidal functions times my exponential function that's decaying. It's true in this case as well, where I have these two exponentially decaying functions. T gives us a little bit of sort of pushback in some sense. And this is that critical damped system that we were talking about, which probably isn't something we observe in the actual world. Critical damping is sort of a pipe dream, more or less. But thinking about this, so this first term definitely goes to 0, but thinking about the second term along with L'Hopital's rule, the exponential function will end up winning and dragging everything to 0. So this is going to head to 0 as well. So in both of these cases, we're headed to 0. But let's talk about the third possibility. So the third possibility is if c squared minus 4 times k times m is positive. So now that means under my square root, I have something meaningful I can work with. We can actually show that in this case, both roots are still negative. And let me sort of explain it this way. Let me jump down here to where I got some more space. I want to point out that c squared is larger than c squared minus 4 times k times m. And we said at the very beginning that m, c, and k are all positive. So here I'm really comparing c squared with c squared minus something that's positive. So here I'm subtracting away something from c squared. So of course this is going to be smaller. Now, if I go ahead and take square roots of each side, we'd say, well, square root of c squared is still going to be greater than square root of c squared minus 4 times k times m. And then at this point, we'd say, well, square root of c squared, that's going to give us c greater than square root of c squared minus 4 times k times m. But now if we sort of think about how this is being constructed, we said that for our solutions, we have negative c plus or minus the square root of c squared minus 4 times k times m all over 2m. And really we're focusing on the numerator here. We'd say there's two possibilities that this will break up into. One of which is where I have the subtraction, right? So let me actually do the minus sign first. So negative c minus radical c squared minus 4km all over 2m. And it's not too difficult to see that this is in fact negative. I have, remember, these things are positive things and I'm subtracting them. So a negative something minus something, it's going to be negative, right? So this is negative. But in the other case where we're adding, I don't mean to wave my finger at you, I'm just very excited. We have negative c plus the square root of c squared minus 4km all over 2m. And what did we say? Well, we said that c is larger than radical c squared minus 4km. And here I have this minus sign attached to it. So which of these outweighs? Negative c, since c is larger in magnitude, negative c wins. So even though I'm adding something positive to it, it's not large enough to change the sign. So this gives me, we could say, sort of the smaller negative value, but still negative. So in each case, now I have negative roots, which, sort of thinking about it in general, my solution in general, whatever you want to call these, here I'll just nickname them A and B, they're negative numbers. But my solution in this case would be some coefficient c sub 1, e to the, since they're negative, let me put that minus sign there. So let me say A is the magnitude, B is the magnitude, but they're both negative. So e to the minus at plus c sub 2, and then e to the minus bt. For example, right, these are negative values that I have in the exponent. So this is another case where, sure, as t goes to infinity, x is going to head to 0. So in any three of these possibilities, when talking about this system, since m, c, and k are all positive, if we sort of explore this with the quadratic formula, we'd say if I get imaginary terms and it builds a sinusoidal function, that's going to head to 0 as t goes to infinity. In the case of repeated roots, where we have that critical damping, this is going to head to 0 as well. And so I can use L'Hopital's rule to show that in its entirety. And if I have the case where the stuff under the square root is positive, giving me two distinct real roots, both of those roots, I should be able to show that they're going to be negative. So then in this case, I just have some decaying exponential functions, and then that's going to go ahead and go to 0 as well as t goes to infinity. Okay, so why is this important to mention? Well, when I introduce a forcing function, so let's go back to our model and say mx double prime plus cx prime plus kx equals some forcing function, and this could be something sinusoidal. It could be cosine, it could be sine, it could be both of them, cosine and sine both making an appearance. When we took a look at this in the section, I think we said f sub 0 and then cosine of omega t. When we build our solution for this, there's two pieces to it, right? X at t is equal to the complementary solution and the particular solution. And remember, this complementary solution, what do I like? Let's give red a shot here. This complementary solution is the solution to the homogeneous variant. So same differential equation, but set equal to 0. And that's this complementary solution. Whereas the particular solution refers to working with the method of undetermined coefficients to solve for the non-homogeneous variant on this. Now, we refer to these a bit differently. So we give them different names. So we say x sub c is called x sub tr, which is a transient solution. And the particular solution, different sources call it slightly different things. Sometimes it's referred to as a steady state function. Our text refers to it as, and I'm more familiar with, x sub sp, which is a steady periodic function, I think is a good way to call it. The steady periodic solution. So instead of using this familiar nomenclature, the complementary solution, the particular solution, we actually give these new nicknames. They still refer to the same principle, but we say, well, now the complementary solution, let's refer to it as the transient solution. And the particular solution, we refer to this as the steady periodic function. Okay, so why does this matter? Why do we call them these? Well, we showed that when I solved this homogeneous case, that what happens, and this is talking about the complementary solution, what happens to these pieces in the complementary solution is that as t goes to infinity, this complementary solution goes to 0, or here we've named it differently, but it's still the same thing. The transient solution goes to 0. That's why we call it a transient solution. This homogeneous solution doesn't really stick around for very long. And in fact, as t goes on, eventually that part of my solution dies off. It goes to 0. So it doesn't really have, we would say, a winning influence on the system. However, since I have this non-homogeneous system, I'm talking about something with a forcing function, something sinusoidal, it's that forcing function, this machinery, that's going to wind up dictating the behavior. So at the very beginning, there might be some small, perhaps somewhat negligible influence from the transient solution. But at the end of the day, as this sort of continues on, as t continues on, the steady periodic solution is going to wind up winning. And how is that steady periodic solution going to look? Well, hey, I'm glad you asked. So now, there's a couple things that I want to talk about, but if we were using the method of undetermined coefficients, and we started with a very important statement, we'd said, let omega not be equal to omega sub 0, where omega sub 0 would refer to a frequency of the homogeneous solution. So if that's the case, then how this particular solution, also known as the steady periodic solution, would look, as a guess, it would be some a cosine omega t plus b sine of omega t. And we actually went and talked a lot about building this into just one trigonometric function, where this would give us some coefficient capital C on cosine of omega t minus alpha. So just writing it as one sinusoidal function. And this function is going to wind up dictating the behavior as sort of the long stay. So the steady periodic solution, as t goes on, these transient pieces to the solution die off, right? They're going to decay as t heads to infinity. Whereas as t goes to infinity, this piece shouldn't die off. It's going to keep oscillating. This is going to dictate the behavior. So that's a little bit behind the nomenclature. Why do we refer to these as transient and steady periodic solutions? But there's something further that I want to discuss now with this sort of mentioned. We talked about practical resonance back in the lecture. Practical resonance is a maximum on this amplitude for the steady periodic solution. But I want to move away from practical resonance and talk about something known as resonance disaster. I want to talk about how we could sort of think about this occurring in our system as well. And let me start with a few colloquial examples of where we would see, resonance disaster. And I'm sure you've maybe heard stories about it. Imagine that you are at a party, a gathering, and somebody has a nice glass of non-alcoholic wine, and they're just about to enjoy drinking their non-alcoholic wine out of their non-alcoholic wine glass. And all of a sudden, you feel an urge to sing. So you start singing, you go, and if you're singing at a frequency that mimics the natural frequency of the non-alcoholic wine glass, then you could cause that glass to shatter. And it's interesting to think about, glasses and things that we would drink from as having their own natural frequencies. You can try to determine what this is by pinging on the glass, giving a little flick. A little flick will do. But that's one of the most common examples. Another common story that's brought up is some sort of alleged bridge collapse where soldiers were marching over a bridge in lockstep, sort of marching across the bridge all together. And the marching mimicked the frequency of the bridge and caused the bridge to collapse. And this, of course, is something that architects will need to take into account. There is a natural frequency to the bridge just existing as a structure. So now this sort of, tale is now attributed to why marching soldiers will break lockstep when going over a bridge. They don't want to create any issues. But also important to mention that now building bridges involve a lot of damping to try to eliminate this possibility of resonance disaster, right? And certainly heavily damped systems don't really have a large threat for this quote-unquote resonance disaster. But those are maybe two examples that you're already familiar with. Let's talk about how this could manifest in a system, because that's very interesting. And it has everything to do with this disclaimer that we've been saying. Make sure that omega is not equal to omega sub 0, where omega sub 0 refers to the frequency of the homogeneous system. And let's just talk about this. I'll try to present it quickly because I'm not trying to make this video super long. I appreciate it if you're checking out my content though. So let's say that we had just a system, let's say that our complementary solution, or well, let's say we didn't have damping. I think that's an important place to start. Because if we have damping, then I think we're going to be pretty lucky to be able to avoid resonance disaster in most cases. But let's say that I didn't have a damped system. Let's say I had mx double prime plus kx, and then let's say I had some forcing function, just like we said before. Now in this case, if I were to solve the homogeneous system, mx double prime plus kx equals 0, well, this would give me mr squared plus k equals 0. And then if we go to solve for r, we'd say, well, here I can subtract k over, so mr squared equals negative k, divide by m. R squared is negative k over n. And then r is plus or minus the square root of negative k over m. Since we said k and m are positive values, certainly this is now negative k over m under the square root, which is going to mean we have imaginary values. So this is actually the same as radical k over m plus or minus radical k over m times I, which is going to build these sinusoidal solutions. So we would say the complementary solution then, that's some coefficient c sub 1 cosine of radical k over mt plus some c sub 2 sine of radical k over mt. But what if this frequency, radical k over m, happened to be equal to omega from my forcing function? That would be a problem. So if radical k over m is equal to omega, we're going to have a problem. And why is that? Well, this means now that my complementary solution is c sub 1 cosine of omega t plus c sub 2 sine of omega t. And then when I go to make my guess, so if I'm trying then to make a guess in terms of my forcing function here, and it could have just cosine, it could have cosine and sine, whatever, we would say in general, we would then make a guess that the particular solution, or the particular solution in this case, would be some a cosine omega t plus b sine of omega t. This is a big problem because these are now linearly dependent. So we'd say, well, hold on. So these things shouldn't be overlapping in this way. They shouldn't be competing for the same function. So what would I have to do to fix the guess? Well, to fix this guess, we would have to multiply all of this by t. So now we have a times t times cosine of omega t plus b times t times sine of omega t. And this is now linearly independent, so this is a fixed guess. So this should work now, since it's not linearly dependent against the homogeneous solution. But that smiley face is not really supposed to be a smiley face. This presents a huge issue. So let's go ahead and assume we go through this process, everything seems fine, we solve for a and b, they're just some constant, whatever. And now I have this particular solution. I want you to think about this. What happens as t increases to these pieces? Well, the complementary solution, so I can sort of jot an idea up here in blue, as t increases, and this is for an undamped system, as t heads to infinity, this complementary solution, x sub c, oscillates. It's just, cosine and sine, so it's just going to be oscillating, relatively harmless behavior. But since the frequency of the natural system, the free motion system, matched with the frequency of the forcing function, my particular solution is now of this form, this number times t times cosine omega t plus some number b times t times sine of omega t. This is where the issue is, because if I look at what's going to happen here, you would say as t goes to infinity, this particular piece, it does some oscillation, but it also is going to head to infinity in some sense. the cosine and the sine is still oscillating, but notice that it's multiplied by this linear factor t. And this is going to drag everything to infinity, and this is going to create some of that wild, erratic behavior to sort of consider. I'm just sort of talking about this in a colloquial way, so I'm sorry if some of my notation isn't exactly perfect or if the way I'm explaining it isn't 100% precise. But that's sort of the idea in sort of a mathematical standpoint. We'd say, well, this is a problem if these frequencies match up. So if my forcing function, which could be my voice with the wine glass, it could be the way I'm marching over a bridge, if my actions have a frequency that mimic the natural frequency of the glass, of the bridge, of whatever that sort of structure is, then that could create this crazy phenomenon known as resonance disaster, right? So this is when, this kind of behavior is when the wine glass is going to shatter, when the bridge is going to collapse out from underneath us, where you wouldn't expect that to happen, but hey, you got to be careful. So really when sort of, working with building these things or when attending parties with your friends, these are things to keep in mind because you likely don't want these things to happen. But anyways, I think that's probably enough of a discussion here. I don't want to end the discussion, so I'm happy to keep talking about things like practical resonance, resonance disaster is what we're talking about now, and just talking about general solutions and how that comes into play as well over on our course discussion board. So let me know what you think about all this stuff. Let me know if you've heard any stories about resonance disaster or if there's anything that you've sort of studied about this, because I like talking about it and learning about it too. So let me know. And thank you so much for checking out this episode of Behind the Scenes, where we take a closer look and a deeper dive into our course material, and I will see you next time.